So this final recording will be labeled 18B, the endocrine system. And we've already seen we have a fairly complex array of reactions in our receptor tissues that the hormones are acting upon. The thyroid gland provided a number of constant regulation needs. The next gland in line is the adrenal gland, for some reason perched on top of the kidneys, and as with most endocrine glands, showing a clear differentiation tissue types. There is a kind of a dense wrapping called the capsule that encloses two distinct layers. This outer cortex, you can see the columnar cells around a very different appearing middle or medulla. And that we have illustrated over here as we look at the capsule, that epithelial tissue that forms the surface. The different zones of the cortex are shown here, clearly different regions and examples of tissue types. Up here we have the boundary of the medulla, and these define the very different regions of hormone production within the adrenal gland. Again, a table is the best way to approach this. We see the different regions that we did not name before, but the zona glomerulosa, the zona fasciculata, and the zona reticularis are three recognizable regions with different hormones produced to affect different target tissues. So these particular hormones increase, for example, affect the kidneys as the primary target. The mineralocorticoids are affecting the renal management of sodium and water, especially when ADH is present. And that water regulation is kind of adjusting the osmotic balance and the concentration balance of fluids throughout the body. It's also affected by angiotensinogen 2, something that comes from a thing we call the renin cascade. I'll show you that in a minute. The zona fasciculata, the so-called glucocorticoids, cortisol, hydrocortisone, corticosteroid. This may be familiar in some forms to many of you, will affect most cells. It'll cause amino acids to be released from skeletal muscles and lipids from adipose tissue. So it's basically promoting the release of monomers that act as nutrients and as building blocks. In the glucocorticoids promote formation of glucose in the liver and glycogen, and promote the peripheral utilization of lipids. Androgens is a familiar name to us, a sex hormone. They affect, not very important in adult men. This is not the differentiating effect that produces male body parts and male fertility, but it is present in children and women, and so the stimulation of adrenal gland androgens does promote bone growth and muscle growth and blood formation in children and in women. The medulla produces that epinephrine, norepinephrine, the endocrine side of sympathetic nervous response, and we've already talked many times about the activation of the body, especially muscle system, especially lungs, especially heart. And we're not talking here about growth or management of tissue. We're talking about the active, immediate activation and acceleration of activity. Let's go up to the pineal gland. It's at the roof of the third ventricle, kind of in this location. It's at the right at the base of this corpus callosum. You can kind of see where it hangs. This is something that in dissection you can often peel the hemispheres apart and see the location of the pineal gland, a singular unit that's sort of located right on the midline. The pineal gland has these particular cells that produce melatonin. It has many chemical effects, an antioxidant. But and its drug effect as a sleep aid is well known. However, more importantly and more broadly, it helps to set a thing called circadian rhythms, so that a regular schedule sets up a rhythm of rest and sleep. And in its natural state, melatonin is involved in that. I think that circadian rhythms were first named from plants. I don't know if you've ever noticed in houseplants or in garden plants, plants often hold their leaves so that the sun shines directly on them. And as the sun goes across the sky, it will change. It's able to change so that the leaf continues to point toward the sun. Small plants will often drop their leaves at night, so they're hanging more straight up and down, and lift them during the day so that there's more surface area exposed to the sun. And the other thing that you'll see, if it lifts those leaves up, and on days like this where it gets tremendously hot and loss of water becomes a problem, it'll drop them back down. Kind of an interesting illustration of a circadian rhythm. Some house plants go through this: raise your leaves in the morning and drop them in the evening cycle. And if you take some of those plants and put them in a closet or in a dark place where you can walk in and look at them, you'll actually notice that for a few days, those plants will raise their leaves at about sunrise and drop them at about sundown, maintaining that rhythm. It's supported by a hormonal production, and the timing of it kind of decays if you leave it in the dark. However, it's reinforced if you leave it in the light. It keeps up that system. So melatonin is something, and the pineal gland is something that we do know several features about, and certainly sleep cycles are a part of that. But it's now being implicated or suspected to have some reproductive effects. The pancreas is a glamour gland of this decade. We defined the pancreas's role producing insulin and glucagon earlier. We noticed that the disease diabetes went from a minor, a lower frequency disease called childhood diabetes or juvenile diabetes. We now have changed that name to insulin-dependent diabetes if the pancreas loses the ability to produce insulin. The way that happens is that the immune system of the body, in an autoimmune reaction, attacks the actual cells in the islets of Langerhans that produce insulin and destroy them specifically. And that produces a type 1 or insulin-dependent diabetic. Now, its effect on regulating the blood sugar is now well understood, and the availability of exogenous insulin has allowed us to maintain diabetics, type 1 diabetics, indefinitely. And often, given our better techniques now for measuring blood sugar and regulating it on an almost hour-by-hour basis, gives us an ability to control that blood sugar better and suppress the effects of insulin absence. Now, more commonly, there's a disease that's usually associated with obesity, usually associated with every disease that occurs in humans. Most every disease is affected by a diabetic condition called type 2 diabetes. You have that, then your prospects of a more serious disease and or mortality go up. In this case, some cells retain the ability to make insulin. There's still insulin in the body, but the sensitivity to that insulin decreases. And so we handle type 2 diabetes routinely with oral medications that are meant to enhance the sensitivity of the body to the reception of the insulin that is being produced. The pancreas sits here in the retroperitoneal space, kind of in this cradle formed by the duodenum, the first few inches of the small intestine. And as I said, this is behind the peritoneum. The stomach passes the material from the stomach down into the small intestine. It's basically popping out behind the peritoneum in that space. Kidneys are also in that space. And at this point, it pops back in. But when it's outside, a duct from the liver, the common bile duct, joins with a pancreatic duct to produce this outlet that is going to deliver the digestive juices to the food stream as it moves by. The insulin is there for the utilization and regulation of glucose levels. The glucagon will be, whenever glucose is high, insulin will be released. Whenever glucose is low, glucagon will be released. The bile is going to be there to emulsify the fats in the diet and to distribute them down to a form we call triglycerides, and eventually to fatty acids in the cells, where they're very efficient at making ATP. The blood glucose story is a carbohydrate mechanism essential to the body. Blood glucose is regulated in the body. This particular diagram says 70 to 110 milligrams per deciliter is the normal range. Different diabetic treatments and different patients will cause for tighter or looser regulation. If blood sugar rises, as it does every time we eat a meal, we get a spike of blood sugar. The beta cells in the pancreas secrete insulin. Now, insulin's effects are too numerous to name here, but since we're only talking about blood glucose, insulin affects the rate of glucose transport into target cells. So it is actually a cofactor in getting the glucose into the cell, and in its absence, that means the glucose stays out in the plasma, circulating in the blood. Blood sugar goes up, 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 and in general, without insulin, you can't get those carbohydrate molecules into the cells. The rate of glucose utilization in the cell and the rate of ATP production goes up in the presence of glucose. The conversion of glucose to glycogen in the liver especially is occurring at a faster rate in the presence of high glucose and insulin. But look at this. The other nutrients, amino acid absorption, the precursors of proteins, and protein synthesis increase in the presence of glucose. Much of that is due to the transport in and out of the cell. Triglycerides, a form of fat in the digestion cycle of fats. Making triglycerides in adipose tissue, so depositing extra energy into fat cells, is accelerated by glucose. Look at those multiple effects, all of which are on carbon fragments that we would call nutrients. Now, each of these then would cause the blood sugar level to drop and restore us into these normal levels. So what happens, by the way, this is what we call the absorptive state. We eat a meal, our blood sugar spikes every time. So insulin is released to control it and also produce these good effects of feeding. But within an hour and a half after a meal, we've absorbed the great bulk of all the nutrients that food contains. So what happens as the blood sugar starts to diminish and drop? We reach that lower level, and the alpha cells in the pancreas secrete the complementary hormone called glucagon. Now, what glucagon does is it takes the glycogen that you just made in the liver, and in some cases, glycogen that's stored in the skeletal muscle, and it breaks it down to glucose and puts it in the bloodstream. So as the glucose starts to fall, the glucagon restores the flow of glucose into the bloodstream. The breakdown of fat to fatty acids in adipose tissue is increased by glucagon presence too. In fact, we find at rest most of our metabolism is supported by a constant flow of fatty acids. The synthesis and release of glucose by the liver, and this is not, again, taking the glycogen apart. We did that up here. Glucagon stimulates the liver to actually take other monosaccharides. So fructose is a great example. It's not blood glucose, but it can be converted to glucose in the liver, and glucagon provides that catalysis for that transition. So all of these bring this back up. A normal pancreas will keep this range, even though you think about the difficulty of that. Here we are dumping huge number of calories in terms of carbon fragments and making a lot of glucose after a feeding episode, and yet somehow it stays in this range. Alpha cells, beta cells, delta cells, and F cells, all of these active in endocrine and hormone regulation. This is a typical picture from diabetes mellitus, the common form of disease that you will encounter in your medical practice, because the combination of, number one, keeping type 1 diabetics alive, and number two, treating the burgeoning number of type 2 diabetics that are developing, means that more and more and more people in our society are living with insulin reduction or insulin absence and the disease diabetes. So what happens when your blood sugar is fluctuating wildly? We do see circulation problems produced by this blood sugar fluctuation. It can produce specifically degeneration of the capillaries in the eye and hemorrhaging in the retina. In fact, a common focal exam that's done on diabetics is to look at their retinas, because it's not necessarily indicating when or if you'll go blind, but diabetic retinopathy, the decline of the retina, indicates that there's problems in other organs and other places in the body. If you look at the retina and the retina is clear and healthy, that's a very good indicator that other problems are at a minimum. Because of the pressure of fluctuating blood sugar, the heart works in an irregular way, and it leads to cardiac circulation problems and blockages, and an increase in heart attacks. Just the first of an example of heart attacks are a major killer. If you have diabetes, your prospect of having a heart attack goes up. Kidney degeneration, because you're changing the osmotic balance in the glucose and because your cells are being deprived, leads to kidney degeneration. Diabetic nephropathy, and that can lead to kidney failure, a dangerous condition for diabetics. Peripheral nerve problems, especially in the fingers and toes, result from compromised blood flow and a number of neural problems with peripheral nerves and regulation being affected by this irregular delivery of blood. Peripheral tissue damage, especially later in life, can lead to tissue death, ulceration, other effects on the skin, being more open to infection as the white blood cells traveling through the tissue diminish, and even to eventually tissue death to the point of amputation of toes or feet. Hormones produced by other organs and other systems will primarily be discussed next semester, and that will be as a result of our parade of organ systems that begin with cardiovascular and then go to lymphatic, digestive, respiratory, and there's actually a physiological chapter on metabolism and energy production. We then go to urinary, And then there's another physiological chapter on fluids and how they're kept in balance. Finally, the reproductive system will round out that role. But right here, the intestines produce many hormones: secretin, gastrin, cholecystokinin. These are regulatory hormones that introduce a new kind of regulation, in contrast to the nervous system and endocrine system, which has an overall network that covers the whole body. The organ systems of the second semester have a significant amount of local control. So produced in an organ of the digestive tract like the intestines, and the primary targets being other organs, whether you're activating the next section of the tract for the food that's coming their way, or you're shutting down the previous section of the tract because the last of the food is moved through it. Examples of local control. Kidneys are involved in water balance and all the concentrations, and that includes everything from the blood, constitution of the blood, to the constitution of the lymph. Ionics affect the transmembrane potentials of cells, and osmotics affect the water content, hypotonic or hypertonic pressures. The heart has effects on water balance because it affects blood pressure and blood volume. So kidneys, hypothalamus, and the adrenal gland are all involved in that regulation. The thymus and the many thymosins that it contains have effects on white blood cells and other cells, especially in the immune response and the protection of the body. Gonads, we're going to have 2 full chapters on that. But sex hormones produce not only the function of the reproductive system, what kind of gamete do you make, but the accessory organs and tissues that will allow you to perform your role, the role appropriate to your gender in reproduction. Adipose tissue, in fact, has feedback to the hypothalamus, kind of indicating the state of nutrition and the release of nutrients. And it is one of these dispersed tissues, that, and the leptin that it involves affects the mobilization of energy and digestion in the body. The kidneys have an endocrine function because of their effect on water balance. We make a liquid excretion that comes out of the kidneys, urine. Primary job, remove that pesky ammonia that comes out when we digest amino acids. We also see the production of materials that is an effect on the kidneys, but actually begins with the exposure of the integument to sunlight. This cycle over here is focusing on the absorption of calcium and phosphate from our food. Now, calcium and phosphate are used in many places, but especially in bone. So things like osteoporosis are affected by this. If sun falls on your skin, cholesterol in the skin makes cholecalciferol. Now that works through an intermediate form of the liver and stimulates the kidneys to make calcitriol. That particular product goes through the blood and in cooperation with parathyroid hormone stimulates this digestive tract, the small intestine, to absorb calcium and phosphate. Now, without this, normally, this is a small amount of sunlight. I keep reading. Some people say if your skin receives direct sunlight 10 minutes 3 times a week, that produces a lot of this hormone. Now, another effect that comes through the kidneys is blood pressure and blood volume, because the concentration of your urine will decide whether you're releasing water or whether you're retaining water, and that's got to be variable. So you think about it, you come and you didn't bring your water bottle, and so you go out and the day is hotter and you sweat a lot. Your kidneys are going to be shutting down that urine production and making really concentrated urine to retain the water that you have in your body. Whereas on the way home, you stop at the bar, you drink 10 beers in an hour, you know you're going to be popping up and going to the restroom, popping up and going to the restroom, because you're going to be releasing high volumes of water. That's an effect that the kidney has. So let's look at this condition of blood pressure and volume, which must vary with our daily habits. If blood pressure and volume are falling, then the blood flow and the oxygen arrival in the kidney go down. That causes the kidney to release two hormones, erythropoietin, EPO, and renin. They have different effects. I'm going to do renin first because it actually is a cascade. Look at this. Renin turns angiotensinogen to angiotensin 1, which turns into angiotensin 2, which turns into aldosterone and ADH secretion. It also stimulates us to, wait a minute, I'm thirsty. So we drink water. So fluid intake is one effect of this renin cascade. The effect of ADH is on retention of water in the kidneys, and the effect of aldosterone is the same. So it concentrates the urine more and more and causes the body to hold on to the water it has. But the stimulation of thirst and the addition of water causes an actually increase in blood volume. That can happen pretty quickly. Both of these contribute to rising blood pressure and volume, but we're not done yet. Back here, where the EPO was released, its effect is on the red bone marrow. And that red bone marrow causes red blood cells to be produced at a higher rate. Now, we're always tearing down red blood cells, huge numbers in the body. But if you think about a dial on the wall that goes from 0 to 10, normally our red blood cell production is at about 2. Pretty constant, but low. Erythropoietin bumps that up. Now, you can bump that in a number of ways. Let's say you exercise heavily. Let's say you're going for maximum fitness. Let's say that you move to Colorado Springs, and all of a sudden you're going from around here at 700 feet to Colorado Springs, and west of Colorado Springs, you're living at 9,000 feet, and the oxygen tension is all of a sudden low. That causes erythropoietin to be released. And the hematocrit of the blood, the content of the solid portions, the sediment, to go up. But its effect in this model is that this actually, by adding cells, you're adding solids to the blood, and that increases the blood volume and the blood pressure. Together, these restore blood pressure and blood volume. The reproductive system is famous for its sex hormones and for the effects that it has. A complex interaction from the hypothalamus, its production of oxytocin, and its releasing hormones that act on the pituitary, with the follicle-stimulating hormone and the luteinizing hormone being the first release, and the direct effects being on target tissues, including the gonads of individuals of different genders. Endocrine malfunctions. We do find that if we are low on certain hormones, it produces certain dramatic effects. Some of these are very dramatic. Growth hormone, underproduction or tissue insensitivity from pituitary failing to grow. Principal signs are slow growth, very little fat distribution, low blood glucose, hours after a meal, and so forth. Overproduction of growth hormone produces a giant, a physiognomy, and acromegaly. Principal signs and symptoms of this are excessive growth. Antidiuretic hormone, diabetes, and a syndrome of ADH secretion abnormality result from that. T3 and T4, we see different levels of metabolic rates established. Low metabolic rate for underproduction. The body temperature can be low, and physical development as well as mental development can be slowed down. If your thyroid levels are too low, if they're too high, you have the opposite effects, high metabolic rate and higher body temperature. This list goes on, and because of the lateness of the semester, I'm not going to go into the specific pathologies of individual hormone deficiencies shown here on the left, or hormone excesses shown on the right. These can be associated with different genes that they work in concert with. So if you have a certain genotype, it may amplify a particular physical effect in the development or in the long-term management of metabolism. This is one thing I need to mention. The idea here is using steroid hormones to enhance athletic performance, something that was discovered as a true enhancement beyond simple conditioning and relying on your own genetic endowment. You can add steroid hormones, and those hormones cause abnormal development of muscular tissue and of the bone tissue that it relies on. That development affects not just the size and the weight of the muscles, but it enhances their reaction times as well. So this is a very popular technique for athletes who are looking for every edge, because winning means contracts and contracts means money. It also means records. It also means, what do they call it now, legacy. Here in St. Louis, we've just been involved in this discussion because the decades-old record for home runs in a single season held by Roger Maris was broken by one of our local hitters. And he's a very large man, very muscular man. And Big Mac Land forever preserves our devotion to that era in Cardinals baseball. Perhaps I'm going on and on about this because I think today is the day we resume play of professional baseball, and the Cardinals will have their first game soon. But the point is that this is considered an external application, and it's very, very hard to regulate because of the complexity of the endocrine system. When we prohibit a drug, we prohibit a specific drug with a specific formula, when in fact further experimentation shows you that a slightly altered form, which is not on the list of prohibited drugs, can produce some kind of enhancement of athletic performance and of muscular proficiency. So given the tendency to cheat and what it means, the tendency to find new and better ways to enhance your performance will continue to be a problem. In general, hormones have an impressive array of enhancing and retarding effects on our everyday metabolism, and it affects not just our regular day-to-day operation, but all conditions that we meet. The general adaptation syndrome is a phrase that refers to our response to recurring or ongoing stress, whether it's emotional stress, it's physical exertion, whether it's threat, abuse, malnutrition, those kinds of things. And if you begin with a healthy person with a healthy body, they go through different phases during which the metabolism of the body adjusts to that level of damage. The alarm phase, you can call this fight or flight. This is sympathetic stimulation. There are huge reorientations. You're going to flow your blood in a different pattern. You're going to work your muscles, heart and lungs faster to take care of the immediate short-term response to crises. But if it does not continue, if it truly is an emergency, and you either escape or you win the fight quickly, there's few long-term effects. If it continues, however, longer than a few hours, you go into a resistance phase. Now, glucocorticoids are the dominant hormones of resistance. Epinephrine, growth hormone, thyroid hormones are also involved, and energy demands are remaining higher than normal, producing a kind of a new cycle of response. Now, resistance is going to have some long-term metabolic adjustments. The remaining energy reserves in the body that were not mobilized by that short-term emergency all of a sudden begin to be mobilized and used. But that means your supply of energy is pretty good, at least at the beginning of this. Glucose is conserved. Peripheral tissues begin to break down lipids to obtain energy. Blood glucose concentrations elevate. Liver synthesizes glucose in greater amounts and from other carbohydrates, from amino acids, and from lipids. So the versatility of the liver in keeping the blood glucose level high. Remember, blood glucose is not only maintained, it's the only nutrient the brain can use. So we're taking care of the brain during this period of stress and decline. We're going to conserve salts and water. We're going to lose potassium and hydrogen, and resistance can go through any number of stages and back and forth. If you reach a particular level of utilization, if that stress and that exertion continues for long periods of time, combined with malnutrition or undernutrition, you reach a stage called the exhaustion stage. Now, this is where the lipid reserves are exhausted to the point where they no longer can support basic metabolism, and you start to suffer damage in organs, first in the peripheral organs, but increasingly in the exhaustion stage to more and more vital organs. You can no longer produce glucocorticoids. Your electrolyte balance starts to fail, and this leads to collapse. Now, during this time, the body's doing its best to regulate the blood flow to vital central organ systems and deprive those organs that are not so central to survival, but eventually you lose control of those and you die. Now, this picture shows the vulnerability. This is probably a mother and child. And what you see here is the mother is very thin, but showing, an amount of healthy tissue, but holding a child that is wasted to the point of starvation. So this child's body is entering the exhaustion phase. The distension of the proportions of the body are a reflection of that. The body's trying to compensate and keep it alive. So on this particular final lecture, final chapter of the endocrine system, I want to call attention to what's been at the end of your chapters all along, this system integrator. And for the first semester, it's a good idea to now go back and read these body systems up and down, pointing out what I think are many of the major relationships. So we covered integumentary, skeletal, muscle, nervous, and endocrine. But this takes a different view, trying to show how each of these systems relates to these other systems in the maintaining the overall health and the homeostasis of the body. So I refer you to that in the end of the chapter in your text. I also refer you back to that first orienting slide that allows you to identify the major locations of hormone production through either glands or distributed tissues in the organs of the body. These are the source of the endocrine hormones that regulate most of the homeostasis and metabolism and many of the ongoing metabolic relationships in our body. Be sure to know these anatomical designations very well. So, are you happy That's the last recorded lecture, which will appear as 18B, the endocrine system.